Electric current is fundamentally the flow of negative charge. Within a metallic conductor, the electric current is transported by electrons. These electrons inherently possess a negative charge. When a voltage is introduced and applied to a conductor, it generates an electric field that prompts the electrons to move. This movement of electrons through the conductor constitutes what we perceive as electric current. It's important to differentiate between the actual flow of electrons and the conventional current direction. Historically, the convention for electric current was established before the discovery of electrons as the primary charge carriers in metals. Consequently, conventional current is depicted as flowing from the positive terminal to the negative terminal, which is the opposite direction of the electron flow. To elaborate further, consider a simple circuit consisting of a battery, a resistor, and connecting wires. The battery provides the voltage that drives the current. The electrons, originating from the negative terminal of the battery, traverse through the connecting wires, pass through the resistor, and ultimately return to the positive terminal of the battery. This electron flow is the true electric current. However, the conventional current is represented as flowing from the positive terminal through the resistor and back to the negative terminal. Understanding this distinction is crucial for comprehending circuit behavior and analyzing electrical systems. The electron flow is a physical phenomenon, while conventional current is merely a convention used for circuit analysis. In most practical applications, using either convention yields the correct results as long as consistency is maintained throughout the analysis. The concept of electric charge is also fundamental. Electric charge is a fundamental property of matter that causes it to experience a force when placed in an electromagnetic field. There are two types of electric charge, positive and negative. Like charges repel each other and opposite charges attract. Electrons are negatively charged, while protons are positively charged. The magnitude of the charge on an electron is equal to the magnitude of the charge on a proton, but their signs are opposite. The unit of electric charge is the coulomb. Electric current is defined as the rate of flow of electric charge. It is measured in amperes, where 1 amp is equal to 1 coulomb per second. Flow of electrons is not always uniform. In alternating current or AC circuits, the direction of electron flow reverses periodically. In direct current or DC circuits, the electron flow is in one direction only. The speed at which electrons move through a conductor is called the drift velocity. The drift velocity is typically very slow, on the order of millimeters per second. However, the electric field that drives the electrons propagates through the conductor at nearly the speed of light. This is why electrical signals appear to travel so quickly. The conductivity of a material determines how easily electrons can flow through it. Materials with high conductivity, such as copper and silver, are good conductors of electricity. Materials with low conductivity, such as rubber and glass, are good insulators. Semiconductors, such as silicon, have conductivity between that of conductors and insulators. The conductivity of a semiconductor can be controlled by adding impurities, a process called doping. Electric current is also affected by temperature. In general, the resistance of a conductor increases with temperature. This is because the atoms in the conductor vibrate more at higher temperatures, which impedes the flow of electrons. In some materials, such as semiconductors, the resistance can decrease with temperature over a certain range. This is because the increased temperature can free up more electrons to conduct current. The behavior of electric current is governed by several fundamental laws, including Ohm's law and Kirchhoff's laws. Ohm's law states that the voltage across a resistor is proportional to the current flowing through it. The constant of proportionality is called the resistance. Kirchhoff's current law states that the sum of the currents entering a node, or junction, in a circuit is equal to the sum of the currents leaving the node. Kirchhoff's voltage law states that the sum of the voltages around any closed loop in a circuit is equal to 0. These laws are essential for analyzing and designing electrical circuits. They allow engineers to predict the behavior of circuits and to ensure that they function correctly. The study of electric current is a vast and complex field. There are many different types of circuits, each with its own unique properties and applications. From simple circuits that power everyday devices to complex circuits that control sophisticated machinery, electric current is essential to modern life. Understanding the fundamentals of electric current is crucial for anyone working with electricity or electronics. It provides the foundation for further study in more advanced topics such as electromagnetism, circuit theory, and power electronics. The concept of electron flow is also relevant to understanding various electronic devices such as diodes and transistors. These devices rely on the controlled flow of electrons to perform specific functions. A diode, for example, allows current to flow in only one direction. A transistor can be used to amplify signals or to switch current on and off. These devices are fundamental building blocks of modern electronic circuits. The behavior of electrons in these devices is governed by quantum mechanics. Quantum mechanics is a branch of physics that deals with the behavior of matter at the atomic and subatomic level. It provides a more accurate description of electron behavior than classical physics. However, for most practical applications, classical physics provides a sufficiently accurate approximation. The study of electric current also involves the study of electromagnetic fields. Electric current produces a magnetic field, and a changing magnetic field can induce an electric current. This relationship is described by Maxwell's equations, which are a set of four equations that describe the behavior of electromagnetic fields. Electromagnetic fields are used in a wide range of applications, including radio communications, microwave ovens, and medical imaging. The generation and distribution of electrical power also relies on the principles of electric current. Power plants generate electricity by converting other forms of energy, such as fossil fuels, nuclear energy, or renewable energy sources, into electrical energy. The electricity is then transmitted over long distances through power lines to homes and businesses. The design and operation of power systems requires a deep understanding of electric current and electromagnetic fields. The safe use of electricity is also of paramount importance. Electric shock can cause serious injury or death. It is important to follow safety precautions when working with electricity, such as wearing appropriate protective equipment and avoiding contact with live wires. Electrical codes and standards are in place to ensure the safe installation and operation of electrical systems. These codes and standards are developed by organizations such as the National Electrical Code, or NIC, and the Institute of Electrical and Electronics Engineers, or IEE. Electric current is a fundamental concept in physics and engineering. It is essential to understanding the behavior of electrical circuits, electronic devices, and electromagnetic fields. It is also essential for the safe and efficient generation, distribution, and use of electrical power. The relationship between voltage, current, and resistance is defined by Ohm's law. Ohm's law states that the current through a conductor between 2 points is directly proportional to the voltage across the 2 points. Mathematically, this is expressed as voltage equals current times resistance, or volts equals amps times ohms. This law is fundamental to understanding how circuits behave and is used extensively in circuit analysis and design. For example, if a circuit has a 12-volt source and a 6 ohms resistor, the current flowing through the resistor can be calculated as current equals voltage divided by resistance, which is 12 volts divided by 6 ohms, resulting in a current of 2 amps. In addition to Ohm's law, Kirchhoff's laws are essential for analyzing complex circuits. Kirchhoff's current law, or KCL, states that the total current entering a junction, or node, in a circuit must equal the total current leaving the junction. This is based on the principle of conservation of charge. Kirchhoff's voltage law, or KVL, states that the sum of the voltages around any closed loop in a circuit must equal 0. This is based on the principle of conservation of energy. These laws allow engineers to analyze complex circuits by breaking them down into smaller, more manageable parts. For example, if a circuit has multiple resistors connected in series, the total resistance of the circuit is simply the sum of the individual resistances. The current flowing through each resistor will be the same, and the voltage across each resistor can be calculated using Ohm's law. If the resistors are connected in parallel, the total resistance of the circuit is calculated differently. The reciprocal of the total resistance is equal to the sum of the reciprocals of the individual resistances. The voltage across each resistor will be the same, and the current flowing through each resistor can be calculated using Ohm's law. Understanding these basic circuit concepts is crucial for designing and troubleshooting electrical systems. Electric power is the rate at which electrical energy is transferred by an electric circuit. It is usually measured in watts, where 1 watt is equal to 1 joule per second. The power dissipated by a resistor is equal to the voltage across the resistor times the current flowing through it. This can also be expressed as power equals current squared times resistance, or power equals voltage squared divided by resistance. For example, if a resistor has a voltage of 10 volts across it and a current of 2 amps flowing through it, the power dissipated by the resistor is 10 volts times 2 amps, which is 20 watts. Electric energy is the capacity to do work. It is usually measured in kilowatt hours, where 1 kilowatt hour is equal to 3.6 million joules. The amount of energy consumed by an electrical device is equal to the power consumed by the device times the time it is used. For example, if a 100 watts light bulb is left on for 10 hours, it will consume 100 watts times 10 hours, which is 1000 watt hours, or 1 kilowatt hour of energy. Understanding the relationship between electric power and energy is important for managing energy consumption and reducing energy costs. Electrical safety is a critical aspect of working with electricity. Electric shock can be fatal. It is important to follow safety precautions when working with electricity to prevent electric shock and other electrical hazards. Some common safety precautions include wearing appropriate personal protective equipment, such as insulated gloves and safety glasses, avoiding contact with live electrical circuits, using properly grounded electrical equipment, and following lockout/tagout procedures when working on electrical equipment. The NEC provides detailed requirements for the safe installation and maintenance of electrical systems. It covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. Compliance with the NEC is essential for ensuring the safety of electrical systems. Electrical grounding is an important safety measure that helps to prevent electric shock. Grounding provides a low resistance path for fault current to flow back to the source, which causes the circuit breaker or fuse to trip and to energize the circuit. This helps to protect people from electric shock and equipment from damage. There are two main types of grounding: equipment grounding and system grounding. Equipment grounding connects the metal enclosures of electrical equipment to ground. System grounding connects the neutral point of the electrical system to ground. Both types of grounding are essential for ensuring electrical safety. Overcurrent protection is another important safety measure that helps to protect electrical circuits from damage due to overloads and short circuits. Overcurrent protection devices, such as circuit breakers and fuses, are designed to trip and de-energize the circuit when the current exceeds a safe level. Circuit breakers are reusable devices that can be reset after they trip. Fuses are one-time devices that must be replaced after they blow. The NEC specifies the appropriate size and type of overcurrent protection devices for different types of electrical circuits. Electric current is the flow of electric charge. In most materials, the charge carriers are electrons. However, in some materials, such as electrolytes, the charge carriers are ions. Electrolytes are solutions that contain ions. Ions are atoms or molecules that have gained or lost electrons and therefore have an electric charge. Electrolytes are used in a variety of applications, including batteries, electroplating, and chemical synthesis. The flow of ions in an electrolyte is called ionic current. Ionic current is governed by the same principles as electronic current. However, there are some differences between the two types of current. For example, ions are much heavier than electrons, so they move more slowly. Also, ions can have either positive or negative charge, while electrons have only negative charge. The study of electric current is a vast and complex field. It encompasses a wide range of topics, from the fundamental principles of electromagnetism to the practical applications of electrical engineering. A thorough understanding of electric current is essential for anyone working with electricity or electronics. It provides the foundation for further study in more advanced topics such as power electronics, control systems, and communication systems. Furthermore, understanding electric current and its behavior in different materials and circuits is paramount for innovation in emerging technologies such as renewable energy, electric vehicles, and advanced electronics. Continuous research and development in these areas are driving progress towards a more sustainable and technologically advanced future.